Let us now continue in this unit for advanced force models by looking at so-called JKR cohesion. JKR stands for Johnson-Kendall-Roberts forces, and what we're going to look at now is a simplified JKR theory for soft particles. This force model works as follows. As long as there is no overlap of the particle with a wall or with another particle, the force is zero. Only if the particle is overlapping with a wall, we use this radius a here to calculate a non-zero JKR force. This force is then calculated with this equation, and you see it's proportional to this radius a to the power of 3/2. Also, it depends on the stiffness, the effective stiffness of course of the contact, and this surface energy density gamma SED here. The radius a here is given by this equation here, and it must be calculated implicitly because you see it's here and here in this equation. There is an analytical solution that you will find in literature, for example in this publication here. The beauty of this model is that there is only one single parameter, this gamma SET, the surface energy density, and these energies are related to the Hamaker constant. Please note again that we need here a minimum cutoff, which is typically standardized with a couple of angstrom. What is important when we're talking about JKR cohesion is that an overlap is necessary to activate cohesion, because if the particles are not contacting, there is no cohesion force. This is different from the previous model for van der Waals forces. Also, you see, the more the particles are interpenetrating or the particle is penetrating the wall, the force is increasing. So it's proportional to this a to the power of 3/2. That means the more we press the particle towards the surface, the stronger is the cohesion. This is of course a problem for the soft sphere DEM. The reason is that in a soft sphere DEM, we typically choose much softer particles than in reality. And it has been shown that this softness effect is important. It can be to some degree corrected, as shown by this publication here. That's it for the van der Waals type of forces. We will now look at liquid bridge cohesion. Let us first start at the beach. If you're going to the beach, and this is me sitting on the beach of Mallorca some years ago, you will see that if you make sand wet, it dramatically changes its structure. It becomes, as you see, fluffy. If you look closely, you really see the fluffiness that is developing. And the reason for this fluffiness are liquid bridges. We have already heard that liquid bridges dominate the cohesion forces. We now have to ask ourselves, where does the liquid come from? Well, there is the obvious option, option A. Particles are covered by a film or droplets are sticking to the surface of the particles. The classical picture that we should have in mind is that there is a continuous liquid film, and if a particle collides with a particle having such a liquid film, a bridge forms. Of course, this is a simplified picture, however it allows us to start with a simple analytical model, for example. The second option, B here, is that there is capillary condensation. Capillary condensation means that we don't see any liquid on the surface of the particles and they are dry. However, there is water vapor in the gas phase surrounding the particles. And this water vapor condenses at the contact point between the two particles. This is relevant especially if you have very smooth surfaces. However, you will see that this is very difficult to predict, and we will not discuss about this in this unit. Let us now look at classical liquid bridge formation for this option A. So we assume that the particles are covered with a liquid film. Of course, one particle can also be dry, that's not a problem. If the particles then collide, the liquid drains into the bridge and then the bridge is formed and we activate the liquid bridge forces. Of course, before there is no contact between the films, there is no liquid bridge, there is no force. We must take care of this in our DEM simulations. Please note that, of course, if the particles are covered by a thin film, it's enough to say that the liquid bridge force is activated once the surfaces touch each other. We have to also consider that there is a finite flow rate of liquid into the bridge. This has been analyzed by this publication here. However, you will see that it's quite fast. The second important physics of such a liquid bridge is that there is a certain critical separation distance until which the bridge exists. If we go beyond this critical separation distance, we reach the so-called rupture distance. Rupturing means that the bridge is destroyed and liquid flows back into the liquid films on the particle surfaces. Let us now come to the next important question. This is, how large are the forces? Before we really look into the details of the force closure, let us start with some force basics. The first important thing is that you understand there is something like surface tension. Also, it is called interfacial tension, gamma. Surface tension is a phenomenon in which the surface of a liquid that is in contact with another liquid or a gas behaves like a thin elastic sheet. This is caused by intermolecular forces, for example van der Waals forces, but in this case between the molecules. For water, also hydrogen bonds are important. Again, these are intermolecular forces and they have nothing to do with the cohesion forces that we have discussed so far. Surface tension draws the liquid molecules together, hence an increase in the interfacial area requires energy. Thus, surface tension has the units of energy per area, in other words, joule per square meter. A joule is a Newton meter, and you see we can interpret surface tension also as a force per unit length. The second important basic phenomenon that we have to understand is the so-called capillary pressure. Capillary pressure is the pressure difference due to this interfacial tension between two immiscible fluids. This pressure can be calculated by the famous Young-Laplace equation. The equation states that the pressure difference between the liquid in the bridge and the surrounding ambient fluid is proportional to surface tension and the sum of the inverse principal radii of curvature of the surface that forms. The next phenomenon that is a result of surface tension is the so-called capillary force. As there is a pressure difference in the bridge and the ambient fluid, there's a contribution of the pressure and there's also a contribution of surface tension, as you will see very soon. The Young-Laplace equation and the closures for the capillary force assume that there is no flow of liquid. So they are the quasi-static limiting cases. Thus, we have to also take into account forces due to the flow of liquid. And these are typically called liquid bridge viscous forces or just viscous forces. These forces result out of the relative motion between the two particles and the squeezing flow of the liquid in the bridge. To sum up, we have to account for three phenomena if we want to model liquid bridge forces. First, we have to have a closure for the capillary force. Second, for the viscous force as well. And last but not least, we have to provide a criterion for liquid bridge rupture. This is it for this part. I hope you enjoyed it. See you next time.